So welcome back, everyone, for the last talk of the day. And the speaker is Tim Meier from Humboldt University, and we keep twisting with non-commutative n=4 super-Young mills via Drinfel'd twist. Please, Tim.
Thank you. So, first of all, let me thank the organizers for giving me the chance to speak here. So, I will present this work about Drinfel'd twisting the n=4 super-Young mills in a non-commutative way. This is based on work together with my PhD advisor, Stijn van Tongeren. And the plan for my talk today is to first give you a motivation where this Drinfel'd twists of n=4 arise from, why we are interested in them. Then I will explain to you the Drinfel'd twists and how they affect and twist a given algebra. I will give you some examples of deformations for this n=4 super-Young mills that fall into this class of Drinfel'd twists. Some of these examples will be of non-commutative type, so I will explain to you the construction of non-commutative field theories on these examples. These non-commutative spaces and structures also affect the gauge theory, so I will elaborate also on a construction how we can get gauge invariant actions for these deformations. At the end, I will elaborate on the so-called planar equivalence theorem, which enables us to relate planar Feynman diagrams of the deformed theory to their undeformed counterparts. Okay, so first let's start with the motivation. So for me, the starting point is the ADS-CFT correspondence, which in its most famous example relates the ADS5 crosses 5 string to the n=4 super-Young mills theory. Both of these theories are integrable, at least in their planar limit, and are relatively well studied in the literature. As Sibylle was already telling you in before the lunch, on the string theory side, there are a bunch of integrable deformations that have been studied already. One famous class of these deformations is given by the so-called homogeneous Yang Baxter deformations. They take a classical R matrix that fulfills the classical Yang Baxter equation to deform this ADS5 crosses 5 string. This deformation is realized as a twisting of the underlying symmetry algebra, the PSU2, 2/4. And this twist, of course, corresponds to the R matrix that we have chosen to deform the the string. In principle, I'm interested in finding somehow the CFT dual to these deformed strings here. And the natural attempt to look for such a CFT dual is to twist the underlying symmetry of this n=4 super-Young mills with the same twist that appears here for these deformed strings. And then we can ask about the properties of the arising deformed version of this n=4 super-Young mills. Also, how do the observables look like, and whether we have integrability for these theories as well. And at the end, we could hopefully find this deformed n=4 super-Young mills to be the CFT dual of this string theory. The topic of my talk will be basically this green arrow here, so how to get from the n=4 super-Young mills to its twisted version via this twist. So, as I told you, for me, these twists are somehow defining the deformation here. But to understand these twists, we first need to look at the Hopf algebra structure that we can define on a given Lie algebra. So we take the universal enveloping algebra and equip this with this canonical coproduct structure, as well as the antipode and the co-unit to obtain the Hopf algebra structure here. A Drinfel'd twist is then such a twist here that lives in this tensor product of the universal enveloping algebra with itself. We ask this should fulfill some properties like invertibility and expandability and some deformation parameter. And then, so for this twist, for this Drinfel'd twist, we just ask the usual co-cycle condition which is this one. So we just consider this usual these usual twists, these usual Drinfel'd twists here, fulfilling this co-cycle condition and this normalization condition here as well. Right. So this Drinfel'd twist then can be used to define a somehow deformed coproduct, which is this coproduct given here. So we just let this twist acting on a given on the canonical coproduct acting on this inverse twist here. And we now want to have a theory that obeys this twisted Hopf algebra structures with this twisted coproduct instead of the undeformed Hopf algebra structures with this undeformed canonical coproduct. In field theories, however, these symmetry algebras act on fields and on their products. So, for example, when we consider the translation generators, so the algebra of translations, this act as partial derivatives on fields and on their products. So clearly, when we act on this pointwise product with a partial derivative of functions, then this is given by the Leibniz rule. And this can be formalized by using the undeformed coproduct. So we introduce this mu that acts on the tensor product of two functions and is defined to give the pointwise product. And if we now act with an element of the Lie algebra, this big X here, this capital X, on this pointwise product, this is realized as the coproduct of X acting on this tensor product of functions here. Okay, so this somehow means that this product of functions here is compatible with the undeformed Hopf algebra structure. But as I told you before, we want to have structures that are compatible with the twisted Hopf algebra structures instead of the untwisted Hopf algebra structures. So what we need to do is to define a somehow twisted or deformed product of functions so that we have structures that are compatible with this deformed Hopf algebra structure. Okay, so let's do that. The twisted product of functions takes this form. So it's basically just this composition of the pointwise product with this inverse twist here. And if we now look on an element of the Lie algebra that acts on this twisted product of functions, we find that this at the end respects the twisted Hopf algebra structure, since this is acting via the twisted coproduct on this tensor product here. Okay, so this is the structure of the product on functions that we are looking for. Okay, and for simplicity and later use, we just call this the star product and we write F star G. The star product, due to the twist, is now non-commutative anymore, but due to the co-cycle condition of the twist, this is still associative. Okay, so this is the object we need to deal with.
Sorry, just to understand. So this is a rather implicit definition, right? The pointwise product of functions has a very explicit definition by taking the value of a function of a point times the value of a function of a point as a C number, right? And so also the derivative and so on, they can be given very explicit definitions. So are you going also to give us some explicit definition of this product, or is it just going to remain like this?
We will come to that in a moment. Mm-hmm. I mean, in principle, it will become clear when we look at examples for these twists, mm-hmm. because these are relatively well defined, and then we can give explicit definitions of these star products here.
Okay, thanks.
But yeah, up to now, this is just the general mathematical structure behind it. And the next step is then to look at the Lie algebra that we would like to deform. And for n equals 4 super Yang-Mills, the underlying symmetry algebra is somehow this PSC2, 2/4. And this is the algebra we would like to deform. Okay, this PSC2, 2/4 has different subsections here. So it consists of conformal symmetries, which are spacetime symmetries. But we also have some internal R symmetries here that really are just internal symmetries, and we have supercharges. And in principle, we could consider twists that live in different regions of these three parts here. So, for example, there's a well-known deformation of the n equals 4 super Yang-Mills, which is called the gamma I deformation, and this can be obtained via such a twist that purely lives in this asymmetry part here. So just to explain to you the structure, so we basically have three deformation parameters, which are these gamma i's. And we have the Cartan charges of the internal SU4 symmetry. And these are the generators here appearing in this twist, and which is used to deform the algebra. And this twist is then also appearing here, here in this definition of this twist function. Okay, so this then introduces some phase shifts of the interaction terms in n equals 4 super Yang-Mills. Okay, that clearly breaks some of the symmetries, but it's still an ordinary, usual quantum field theory. So we can just consider this as a quantum field theory and calculate observables here. What we are interested in is twists that actually deform this conformal symmetry, so the spacetime symmetry of the theory. And therefore I have two examples of these twists. So the first one is called the canonical twist, and it basically takes translation generators to deform the algebra. In terms of the arising non-commutative structures, this is really the canonical example in the literature. So I will take this as a baby example of what we are really looking in, which is this, what we call the Lorentz deformation, which considers a boost and a commuting rotation in this twist here. And we are interested in this because this commutes with a dilatation operator. So we can hope that we have, or we can at least try to find a calculation of the anomalous dimension, which is still meaningful for such a twist here. Okay, so as I told you already, these lead somehow to so-called non-commutative spaces. But why is that? So therefore, we should look at these generators here in the twist more closely. These are vector fields, and therefore they are already seeing coordinates. And since they are seeing coordinates, we can give such a star commutator between coordinates. And in comparison to the undeformed case, this commutator is non-vanishing anymore. So for the canonical case, this is proportional to this theta mu nu, which is constant, but clearly non-vanishing. Additionally, these generators can act as Lie derivatives on the basis 1 forms. But these Lie derivatives with respect to translation generators here are just vanishing. So this means that the twists don't see basis 1 forms. For the Lorentz deformation, the story is more complicated. So here we have a non-constant commutator, for example, for this star commutator between x1 and x0 and x2. And we also have this non-vanishing Lie derivative with respect to Lorentz generators of these basis 1 forms, which actually means that that the twist sees those basis 1 forms. And since these commutators here are non-vanishing, we call those non-commutative spaces.
If you make explicit this Lie derivative in this Lorentz case, I missed the point. It's just a contraction, d plus d contraction.
So it's really, so these are just defined in such a way.
I speak about Lie derivative. It's defined in the standard way.
Ah, yeah.
d plus di.
Yeah. The Lie derivative is really just the standard Lie derivative here. And these generators here then really just act as the standard Lie derivatives on all the objects. Okay. So now we have these non-commutative spaces. The question is, of course, how we can now define a deformed version of a given theory on these non-commutative spaces, and especially for this n equals 4 super Yang-Mills that we are interested in. And the idea is basically to replace products by star products. And this is because we want to have structures that respect the twisted Hopf algebra structure instead of the usual Hopf algebra structures. And this is always obtained via these star products. So this is the overall idea. And then there have been work for this canonical deformation. For example, there's this review from 2003 from Szabo. that elaborates on this canonical deformation and gives a construction for this, also including a construction for obtaining gauge invariant theories in this non-commutative deformation. There have been work also on trying to generalize this approach for the canonical deformation for deformations beyond this, this canonical deformation. For example, by these collaborations. The problem here is that these generalizations, in principle, do not really work out properly in terms of gauge invariance. So for all deformations beyond this canonical one, up to now it is only possible to find gauge invariance perturbatively in the deformation parameter. So especially there's no all-order gauge invariant theory beyond the canonical deformation. Okay, with our work we somehow found a deformation in which we really can find a gauge invariant action. So we are really somehow solving this problem here for at least some deformations. And before I come to that point, how it works for deformations beyond the canonical one, I would like to recap how the construction works for the canonical deformation. Okay, so the canonical deformation has a property. So this star product is non-commutative, but whenever we integrate over the full space, this star product becomes cyclic again, which effectively means that we can forget about exactly one of the star products in such a row. This has some consequences, like propagators in this theory remain undeformed. So the kinetic action of a scalar field, for example, has just this one star product, which we can forget about. So it's clearly the undeformed action here. Interactions are really deformed. Like when we consider the 5 to the 4 interaction here, this has 3 star products. We can forget about at least one of them, either here in the middle or one of these at the border. And then there are still 2 star products left over. So this is really deformed. The deformation for this theory sits in the interactions. Okay, so this is scalar theory, but what is about gauge theory here? And the problem with gauge theory is that the gauge transformations are affected by the twist. And this is because they are local, so they depend on coordinates, and therefore the twist can act on them. The solution is to define somehow star gauge transformation instead of the usual gauge transformations. So we introduced, for example, for a joint scalar field, we introduced this star commutator as the transformation rule. And with this, we then can define a covariant derivative on this scalar field, which here again appears with a gauge field combined with this star commutator here. And the transformation rule for this gauge field is then again given via a star commutator here at the end. Okay, so this with this construction it can be shown that we can just deform a given action by replacing products by star products, and this star gauge transformation actually lead to gauge invariant actions. So there's a little caveat. So we cannot define this gauge group to be SUN. And this is because the determinant is not compatible with the star product structure. So we cannot consistently set the determinant of such a group to be 1. So instead of this, we consider, for example, the UN as the gauge group. Okay. So this is for the canonical case. Now let's go to the Lorentz deformation. As I told you already, this has a non-constant commutator between coordinates, but also...
Sorry, wasn't that a sinh before? Or?
Yeah, maybe that's a typo then. So,
okay, never mind.
So here, these, as I told you, the twist basically also sees basis 1 forms here. And this is more involving than the canonical case, because it means that we also need to deform the exterior algebra between forms. So basically, we do the same with a wedge product that we did for the pointwise product between functions. We twist it, by this composition with this inverse twist here. And then we just call this the star wedge product between forms. This, due to the non-commutativity of the twist, kills the usual commutation rule between forms. But again, when we integrate over those forms, we recast this commutation rule back. And this is in some sense the equivalent to this cyclicity condition here in this deformation, in this canonical deformation. Okay?
So essentially the symmetry is encapsulated in the integrable relation, right?
Sorry, again?
Antisymmetry of the exterior algebra is encapsulated in this algebraic relation that you show.
So yeah, basically
the last line, yeah.
Yeah, so we need to integrate to find this antisymmetry of the forms again.
Yeah, okay, that's an analog. That's what I'm saying, right?
Mm-hmm.
Of the exterior standard algebra.
Yeah, in some sense. So just to give you an example, so for this Lorentz deformation, the star wedge product between these dx1 and dx2 has a term that is proportional to dx1 wedge dx2, like in the undeformed case, but there's also another term that is proportional to dx0 wedge dx3, which would disappear in the undeformed limit.
What is the basis?
So this basis here in the star product, yes, we can. I mean, we can order this with which introduces some prefactors then that are not true. We can choose a canonical ordering here, and this is basically what we will use in a moment. But first, so this is fine. Okay, we have a deformed exterior algebra somehow, but let's look on gauge transformations. And in principle, we have learned from the canonical case that we need to consider star gauge transformations instead of the usual gauge transformations. So let's do the same. Let's consider an adjoint scalar field and just assign the star commutator as the transformation rule for this scalar field. So then, as the next step, we would like to define some covariant derivative on that. And therefore, we need to look at the transformation rule of partial derivatives of these scalar fields. And here, in the transformation, this partial derivative acts on the star commutator. So basically on star products between functions. But this means that this partial derivative here need to act via the twisted coproduct instead of the usual undeformed coproduct on this tensor products here. Which means that this doesn't reduce to the usual Leibniz rule. So it doesn't give the sum of these two commutators. It gives something more complicated, and especially something that cannot be cancelled by the usual transformation rule of this gauge field that we've seen for the canonical case. So this is a complication, but to be honest, this shouldn't really surprise us because we didn't consider consider here that the twist sees also the basis 1 forms. What we instead need to do is, so yeah, this story here doesn't work out, but what we instead need to consider is we need to formulate everything via forms. And okay, these scalar fields are 0 forms, so it makes sense to stick to this star commutator as the transformation rule. But instead, considering partial derivatives of this scalar field, we consider exterior derivatives. And the reason for that is these always commute with Lie derivatives. And since they commute with Lie derivatives, these exterior derivatives always commute with the star product. Because the twists in the star product act via Lie derivatives on the objects. But since this is the case, it is immediately true that the exterior derivative of a scalar field transforms as the sum of these two star commutators, where the exterior derivative either hit the gauge transformation or the scalar field. And now again we can introduce some gauge field, some gauge 1 form this time, that transformed in this proper way, so that this transformation cancels the unwanted term here, and we can define a covariant exterior derivative. Okay, so this is at least a consistent, a consistent gauge transformation for this Lorentz deformation. But it means that we need to formulate everything in terms of form, in terms of forms, because these seem to be the natural objects here under this deformation. Okay, so but before we can look at the deformation of a given action, we first should look on the behavior of forms under this twist and in these non-commutative spaces. And therefore, first let's look at these exterior derivatives. So in a given basis, they are just defined via this partial derivatives of a function times this basis 1 forms. Okay, that's okay, and this is what it is, but this is not really respecting the twisted Hopf algebra structure. Instead, we would like to have a star product here in between those objects. So we just define a star derivative somehow acting on this field such that this really respects the twisted Hopf algebra structure. And then we can use this equality between those expressions to relate this star derivative back to this untwisted partial derivative. And there appears this operator, this F inverse with these two indices, but this is nothing else than just the twist function, the inverse twist function, where the second leg in this twist is just acting on basis 1 forms. And therefore it just rotates the basis 1 forms in each other, which gives this index structure here. Okay. For general 1 forms, we can do the same. So they are just defined in a given basis with these component fields, but without a star product here. So we just define these star component fields in such a way that this is the basis 1 form in a given basis of basis 1 forms. And then again, we can relate those component fields with each other. And again, this twist with these two indices here, with these two vector indices, is appearing that we are already familiar with from the star derivatives here. So these twists with two indices in this Lorentz deformation look like this. In principle, like a boost and a rotation, where now these transformation angles here are operator valued and act as operators on functions or forms. On this twist, we can raise and lower indices just using the usual metric, which just means we are inverting these operators somehow. Okay, we can also find a commutation rule between basis 1 forms and functions. So we basically compare the star product between a basis 1 form and a function, and the other way around. And this gives such an R matrix here. And since we are comparing two different kinds of star products, we get two twists. And for the deformations that we are looking in, this R matrix is then exactly the square of this twist. So we now can move fields over basis 1 forms. But we could define as well also a commutation rule for moving basis 1 forms over basis 1 forms, which would allow us to order these basis 1 forms as well. Okay, so we have this deformed exterior algebra, and with this we can also define something like a deformed epsilon tensor. And this, like in the undeformed case, just collects the coefficients of the star product of the star wedge product between 4 basis 1 forms with respect to this canonical volume form here. And this canonical volume form is chosen in such a way that it uniquely reduces to the undeformed volume form. Okay, so then we have these coefficients of these with respect to this volume form collected in this epsilon tensor. Okay, so we can also move fields over these basis 1 forms here. When we multiply via a star product a function or a field to the very right here, we can move this over all these 4 basis 1 forms, which introduce 4 of these R matrices. So this one here, and then collecting just the coefficients with respect to the volume form gives this epsilon tensor. On the right hand side, we just have the star product between this volume form and a field. But this volume form is uncharged under Lorentz under Lorentz transformations. And since our twist is made out of Lorentz transformations, this is not seen by the twist. So it commutes with every object. So we can just move a function over this volume form without changing anything. So and this then lead to this equation here, which means that whenever we have 4 such R matrices contracted with this generalized epsilon tensor, this reduces to this starred epsilon tensor. And this is due to the unchargedness of this volume form here.
Is there a top form in this deformed exterior algebra?
A top form. So
You have a 5 form, for example?
so we just have, so we're just considering field theories in 4 dimensions. So this volume form is the,
Yes, but if you take 5 terms like that.
so this is not, there you get 0 because you always can reduce this to this kind of form here, and then you add something additionally, and you can always permute things so that you uniquely get 0. Because whenever you have 2 basis 1 forms, so dx1 star wedge dx1, for example, next to each other, this is always vanishing.
So there is analogous exactness in both, right?
Sorry?
There is analogous exactness in both.
Yeah,
Cohomology.
kind of.
Yeah, for example, cohomology.
Yeah, this, so.
Normally in non-commutative geometry we don't have this feature. You can take, if you deform in non-commutative geometry, normally if you deform the 4-dimensional space, you may have a non-trivial 5 form. So your deformation is such that you don't have 5 form.
So I'm
There exist many deformations, non-commutative spaces. So in your case, there exists a top form, which is a 4 form.
I think so.
Okay.
Okay, so right, we have this relation here. So these R matrices contracted with this epsilon tensor always reduce to the epsilon tensor. We can also use this epsilon tensor to generalize the Hodge dual in a given basis. So the Hodge dual of a basis 1 form, respecting the twisted Hopf algebra structure, is given by this star wedge product between these basis 1 forms instead of the usual wedge product. And also we replace the totally antisymmetric epsilon tensor by this starred version of it. And then this is how the Hodge dual for basis 1 forms look like, but we could also define it for the other forms. Okay, so with this we now basically have all the structure on hand that we need to formulate or to understand the structure of forms on this non-commutative space. So the next step, of course, would be to deform a given action. And therefore, I would like to consider this action here, so a Yang-Mills action and this action of a scalar real adjoint field. So this is written in terms of component fields, and since forms are the natural objects of the twist here, we first need to write everything here in terms of forms. So this is the action, how it looks like, and we then have here this gauge 2 form and the exterior covariant derivative given by this. Okay, so since this is now written in terms of the fundamental objects, we can just deform this by replacing every product just by star products and using the appropriate definitions of the Hodge duals in this twisted deformed spaces. And this is what we get. Okay, that looks pretty nice and relatively good, but the question is still, is this really gauge invariant? And to answer this question, we need to recap some of the properties. So just by construction, we know that the fields transform covariantly under the star gauge transformations. And we also know that this exterior algebra is cyclic under integration. But since this is the case, the Hodge duals should also better transform covariantly to give a gauge invariant action. And this is what remains to be checked. And therefore, we need first to calculate the transformation rule of these component fields here, of these starred component fields that appear in the gauge form. And to get this transformation rule, so this first term immediately follows from this commutator, but the second term, we first need to move this epsilon over these two basis 1 forms. And by doing this, we introduce these two R matrices here. We just get them. So, okay, this is what it is, and this we can now plug into the definition of the Hodge dual. And the first term immediately reduces to the first term that we want to see, but the second term looks like this tiny little mess. But okay, so we can just go on and move this gauge transformation here over these two basis 1 forms, but this time from left to right. So instead of R matrices, we pick up inverse R matrices, especially those two here. And with this first one, we can just lower and raise indices with these metrics here so that they effectively get inverted. So we just have these 4 inverse R matrices acting on this gauge transformation here. But these upper indices here are contracted to this epsilon star tensor. And therefore, we already know that this every time we have such thing appearing, this reduces to this epsilon star tensor itself with these lower indices. But since this is the case, also the second term reduces to the second term needed in this star commutator here. So at the end, we find that this Hodge dual really transforms covariantly under the star gauge transformation, which means that we find a gauge invariant action with this deformation. So, yeah, and this is due to the unchargedness of the volume form, which ensures this relation here. So this is quite remarkable because now we have a deformation in which we can find a gauge invariant action. So we have a deformation beyond the canonical one. So this is really something that was not possible for any deformation in the literature before. Okay, so this is remarkable, but we can do even better. So in n equals 4, so I mean this is just a bosonic theory. In n equals 4, we also have adjoint fermions. And with those, we can proceed analogously to the vector fields. So we introduce some Grassmann-valued, some kind of half forms, these S and S bar that transform under the spin representation, like this. And with these, we treat these psi alpha, so the usual fermionic fields of n equals 4, as components of these objects psi, and simultaneously for these psi bars here. And these are then defined just as the product of these half forms with these component fields, exactly like for the gauge field with basis 1 forms. This again is not respecting the twisted Hopf algebra structure, so we define these start version of these component fields, such that this respects the twisted Hopf algebra structure. Okay, so we can play the same game like with the vector fields. So we can relate these start fields to the unstart ones by having this inverse twist function. This now has spinor indices here, which means that one of the legs is just acting on these basis half forms here, instead of 1 forms. We can also find such a commutation rule between these fields and these basis 1 forms, including this R matrix with spinor indices. Okay. So with this structure now, we can assign gauge transformations to these fundamental objects here instead of the component fields. And when we do this, we can find a deformed action of n equals 4 super Yang-Mills. And we proceed in the same way like we did for the example before. We first write everything in terms of these fundamental objects, so in terms of these forms and these fundamental fermionic objects. To obtain the right component action, in the undeformed case, for these fermionic actions here, we need to integrate over the Grassmann-valued half forms. But okay, so this is then the undeformed n equals 4 super Yang-Mills in terms of these fundamental objects. And this can be immediately deformed by just replacing products by star products. And we can check explicitly that these terms are all gauge invariant, which again gives us this n equals 4 super Yang-Mills for this deformed space beyond the canonical deformation. So that's kind of nice. So this action here has some properties. So when we, for example, consider this kinetic term of the scalar fields, we can choose a basis for these forms and can work out the component fields here, the component field action. When we do this, we arise at this relatively simple looking term. However, this covariant derivatives here include these twists and star products here, where usually we see commutators. Okay, so so since this volume form here is uncharged under the twist, we can again forget about one star product here in this integration. So this then just reduces to the usual d mu phi times d mu phi. And for the term that gives the propagator, we can see that this leads to the fact that propagators do not change as well in this Lorentz deformation here. However, as you can see from these terms here, when we plug them in here, we have these twists and additional star products, which means that interactions are really deformed again, also for this Lorentz deformation. Okay, so since we have deformed interactions, we would need to compute new or deformed Feynman diagrams. But luckily, there's something that is called a planar equivalence theorem, and that is proven in the literature for the canonical deformation by Thomas Filk. This relates the deformed planar diagrams to their undeformed counterparts. And the proof, so here for the phi to the 4, works in the following way. So we take this interaction term and we first separate all these fields in their positions. This we do by integration by introducing this dummy integration here, and then we can keep track of these star products, of the twists in these star products separately. And these indices here at these partial derivatives in this twist keep track of which of these fields these derivatives act on. The next step is then in this proof by Filk to Fourier transform these fields here so that these partial derivatives become just momenta. We also have momentum conservation here, and this is then how this interaction looks like in momentum space. And what changes in comparison to the undeformed case is just this this exponential here, this product of exponentials. So let's take a closer look on that. We can redefine these momenta to be the sum of an ingoing and an outgoing momentum. When we do that, this double product of A and B reduces to the single product, where in this exponent we just have neighboring momenta appearing. And these are appearing in this ordered way because this theta mu nu is antisymmetric. But this can be related to some sort of Feynman rule. So for every external leg for this interaction, we draw these doubled lines where we have one outgoing and one incoming momentum. And for these exponentials here, we draw these arrows pointing from the outgoing to the ingoing momentum for each of these vertices. So these little arrows here always go clockwise. With these, we can now draw planar diagrams like this one. And then we see for these inner propagators here that on both sides of these propagators we have appearing these arrows, but they are pointing in opposite directions, which means they cancel against each other effectively. So that means that we don't have star products between internal propagators. They are just star products between external propagators left, which is remarkable because now we are able to use the undeformed planar diagrams, and multiply these star products on the external momenta afterwards. Okay. In n equals 4 super Yang-Mills, we are more interested in Feynman diagrams directly in position space. But we can do a similar proof also in position space. We first again separate the fields in the vertices from each other, like we did here, but then we directly Wick contract to get to the Feynman diagrams. Then we can use the translation invariance of the propagators to relate the twists from one end of the propagator to the other end. And these lead then to cancellations between all the internal star products. So we are again just left with star products that can be mapped to the external positions. So the proof goes as well in position space for this canonical deformation. In principle, we would like to have something similar as well for the Lorentz deformation. So and here we can follow basically the same steps. So again, we separate the fields in the vertices from each other and Wick contract for getting the Feynman diagrams. But instead of using this translation invariance of the propagators, we use Lorentz invariance of them. Okay, there's a caveat. So for example, when we look at the fermionic propagators, these are not really Lorentz invariant on their own. So when we have this Lorentz transformations acting on this component propagators, this is not vanishing. But as we did all the time, we need to consider the right objects. So which means we should take into account these basis half forms for the fermions here as well. And when we do this, this object here is again Lorentz invariant. The same we can also do for the vector fields as well. But with this together, this Lorentz deformation for the proof of this planar equivalence theorem behaves identical to this proof for the canonical deformation here. So we can really have this proof for this planar equivalence theorem for this Lorentz deformation as well. So we can do Feynman integration. Okay, so I think it's time to recap what we've achieved. So we first constructed a consistent Stargate symmetry for this Lorentz deformation, so for a deformation beyond the canonical one. And we were also able to construct a Stargate invariant action for this Lorentz deformation. So for a deformation beyond the canonical one, which was not done before in the literature. We were able to adapt the planar equivalence theorem for Feynman diagrams as well. So, but when we look at the properties that allows us to formulate this gauge invariance for the actions in the Lorentz deformation, this is governed by basically two properties. The first is the invariance of the volume form, and the second one is the cyclicity of forms under integration. But this can be generalized immediately to twists that fulfill these two conditions, where S is here the antipode, and these are the elements appearing in the Sweedler notation of the twist, and of course the unchargedness of the volume form. So a bigger class of examples fulfilling these properties are, all, for example, all deformations that lie in this that lie in the Poincaré algebra and fulfill this equation. So this is remarkable because we do not just have a construction that works for one particular deformation. We have a construction that even works for a class of deformations. So this is a huge step. But of course, we would like to obtain the integrable structures that we see in the undeformed n equals 4, also here in a twisted way in this deformed n equals 4. And usually in the undeformed n equals 4 super Yang-Mills, the first hint for integrable structures is it can be obtained by computing the one loop anomalous dimension of some gauge invariant operators. So, yeah, therefore we need to construct gauge invariant operators also in our theory. And so this is something that maybe goes too far for this talk, but just to mention it, the problem with these gauge invariant operators is that the usual trace operators are not gauge invariant anymore. And this is due to the non-commutativity of the star product. Instead, we need to introduce operators with somehow twisted boundary conditions that are actually gauge invariant here. And of these, we would like to compute the anomalous dimension, at least one loop, and we would like to obtain the spin change structure, like a nearest neighbor Hamiltonian and the beta equation and beta ansatz in a somehow twisted way. So this is one of the next steps, but another direction would be, of course, to generalize our construction to deformations beyond this class here. So for example, we could consider deformations that include a dilatation operator as a twist, or as a generator in the twist. The dilatation operator wouldn't leave the volume form uncharged, and therefore the construction would break for this twist. And we would like to understand how we can generalize our construction to work as well for such deformations. Okay. Thanks for the attention.
So, are there any further questions? We already had a few, but.
Thank you. So I'm not sure this is a terribly useful question, but just the S alphas look very much like superspace coordinates. I was just wondering, did you look at what happens if you do all this in n equals 1 superspace, and whether there is any...
We didn't look at that, and the reason therefore is that this formulation via forms is something that is already done partially done in the literature, and therefore we just stick to this formulation and just generalized what we had for the fermionic variables as well. And we didn't look on superfield formalism because these non-commutative structures were, like for Kappa-Minkowski case, were studied for theories that naturally don't have supersymmetry. So that was the first thing to look at.
Just related very quickly, the deformations you are looking at, do you know how much supersymmetry they preserve?
That's a good question, but I would say that this deformation breaks supersymmetry completely. I think so. So when we would include the dilatation operator, then there would be a chance to recast n equals 1 supersymmetry, like the beta deformation also preserves n equals 1 as well for deformations in the R symmetry.
Thanks for the nice talk. I was just a bit confused. This epsilon star tensor, should I think of this as just a tensor of numbers?
So it's basically just collecting some numbers depending on the deformation parameter. So just some e to the I lambda, e to the minus I lambdas, or ones or minus ones, depending on these objects here. So for example, when you have dx0, star wedge dx1, dx2, dx3, then this is clearly 1. But when you have something like dx0, star wedge dx2, star wedge dx0, star wedge dx2, which in the undeformed case would vanish, this picks up some sign of lambda.
Right, okay, so it's not totally anti-symmetric in the usual sense.
Right.
Right, okay, thanks.
I just wanted to follow up on Ben's question, because I guess that what you did is not supersymmetric, but rather than touching the dilatation, you could actually combine these with something in R symmetry space, probably, to restore some supersymmetry, I guess, right?
So you mean just considering an additional twist in the R symmetry to recast supersymmetry?
Yeah, something like that. That should be possible.
Well, thinkable, but I would say, yeah, maybe. So yeah, with this,
Yeah, twisted. Yeah.
Well, everything is there twisted.
Yeah. Well, but I guess it would make sense probably to twist their symmetry simultaneously, right? Otherwise,
yeah,
I'm not sure. I'm not sure whether there are any theorems as well for these. I mean, what would be protected and what not. But yeah.
Lorentz is not broken to nothing, actually. There's something.
Yeah.
So there could be some 3D series.
Yeah, that too. Yeah, another question?
Yeah, according to these last questions, in order to have supersymmetry, you need the equation of motion, I think, because you need closure of the supersymmetric transformations. Are the equation of motion computed? Or can you compute it or put stars when you need? Because you said you have an action,
Yeah.
but what happened with the dynamics of that action?
So I mean, in principle, you can find some equations of motions as well, and they should pick up some deformations as well, like taking star products in between objects. I mean, what you can do is, so for these deformations here, you can always forget about one star product under integration. So when you do a variation with respect to some variable, you can always forget about the star product with respect to this deformation, and then you just collect all the other terms, and this is giving you the equations of motion.
And integration by part is compatible with the exterior derivative you have?
That's a good question, but I would think so. Yes, that's true.
Perhaps it's not automatic.
What I said,
Maybe with a microphone.
we have to say something how the field behave at infinity.
Yeah, that's true.
And so this was not discussed so far.
Have you tried to look at Yang-Mills theory on S3 cross R?
So like S3 on cross R, yes. So we thought about looking on this, but the point there is that we have some. I mean, in the undeformed case, we have conformal symmetry. So this should be equivalent to the Minkowski space here.
Right.
But the point is that when we start breaking this conformal symmetry somehow, with this Lorentz twist.
Well, you can keep R still untouched, right? And then you would still have a
But then
invariance in this.
But then we would need to compute field theory on this somehow curved space, and this seemed to be heavier than sticking to this deformation here.
Well, S3 is a reasonably simple space, isn't it? No?
So, I mean, then we have to know all Feynman diagrams on S3.
Mm-hmm.
Like, written in that.
Well, why I'm asking this question, as far as I understood in the planar limit, this deformation is the same as undeformed theory, right?
No, it's not the same. So
No, so then okay, then the question.
So what we have is I mean, in principle, we can compute the same planar diagrams, but
Yeah.
we still need to consider star products acting on the external legs. So this is what really changes.
So
in
what's the
comparison.
effect of this action? Is it just the overall phase for each of these?
So it's
diagrams?
some non-local operator acting on the positions at the end.
Non-local operator, so not just a multiplication by base. So what do we get for a spin chain?
This is an open question up to now. So I mean, we would expect. I mean, we hope to find something that is twisted in the same way, like the spin chain for the corresponding string is twisted, but we still need to tackle this problem for this field theory. We need to do the computations.
Can you comment what is the relation with non-commutative gauge theory of Seiberg and Witten?
So there is this Seiberg and Witten map, in principle. This somehow relates this star gauge symmetry to the usual gauge symmetry, but So we didn't look on that closely because we first wanted to have this construction here for this star-gauge symmetry. So we think that there should be, I mean, there should be a Seiberg-Witten map here as well, but this is clearly non-trivial and just known in, I mean, we could just hope to get the Seiberg-Witten map in some perturbation of the deformation parameter. And therefore, we didn't look in detail on this Seiberg-Witten map here.
What happens with topological terms? So if you take FF dual, since epsilon is changed, so what do you get? Do you still have trivial term, or it becomes non-trivial?
This apparently I don't really know. I mean, so.
And similar question for Chern-Simons. I'm just curious about epsilon.
We haven't looked on something like Chern-Simons. So this is a field theory.
So one last question, maybe.
It's related to this last question. Can you define the F potential? Can you define a curvature using your exterior derivative?
So I mean, this is just the deformation of a quantum field theory. So I apparently don't know the answer.
Okay. And the closure of the transformation, because you have this transformation according to the Lie derivative, and then you deform the gauge transformation in order to be compatible, as far as I understood. And all these transformations generates new brackets, you know, if the closure is guaranteed, ensured.
So yeah, I mean, so that's a good point. But so yeah, in principle, so we have this star-gauge symmetry here, and this is what we get at the end. And, yeah. So I mean, potentially, so you can have some more brackets, but we didn't. I mean, we didn't. Well, I don't know. So I think. So the point is, we have this star-gauge symmetry here that behaves in some sense similar to the undeformed case, but we have this deformed product between these functions here, and this is what we have here in this game.
Okay, that was a very nice talk and also a very nice discussion. Just before we thank Tim again, there will be an announcement by Stein, so don't run away. But let's now give a big hand to Tim and to all the speakers of the day.